So hello and welcome to the first video on the topic of principles of tomographic methods. We're going to discuss computer tomography in this presentation. And this is a CT machine, and although this guy doesn't seem very happy, this is a really cool instrument. We're going to look into how it works, and this actually has a little bit to do with our lab work. Let's get started. What we have here is three different cubes. And inside these three different cubes, I have black squares, which contain, or rather, they don't contain any dense material, and the red squares that contain very dense material. And I can't see inside the squares, and I wanna figure out what is the configuration of this dense material. So I'm looking at the square from the outside, and I have no idea what it contains. What I can do is I can radiate it, and I can put a detector on the other side and see if I detected absorption. And here on the other side, I would notice I detected an absorption of, let's just say, that is equivalent to one absorbed square here. That means I have in this row here, somewhere here, I have one dense square. I'm going to radiate this axis as well, so I'm going to get the same reading. So this means basically that after my reading, I know that somewhere along these lines, there is at each point one dense square. And if I do the same to this square here, I radiate it, I'm going to get essentially the same reading for these two axes, because here I have also one square, and here I also have one square. So this square and this square, if I radiate only in the x-axis, they look the same to me. Let's see what this square looks like. And I'm going to radiate the x-axis as well, and I'm going to get one attenuation here and one attenuation here. And this basically means all these squares, they look the same to me if I radiate on one axis. Let's see what happens if I add the y component. So I'm going to radiate here, and I can actually detect there is an attenuation here. So let's see. I'm going to have an attenuation somewhere along this line, and I'm going to have an attenuation somewhere along this line as well. It just so happens. There we go. So I know that somewhere here I'm going to have absorbing dense material, but I can't really be specific as to where it is, because if I radiate the y-axis on this square as well, I'm going to get one attenuation here and one attenuation here, and essentially these two squares are going to look the exact same to me. They're going to look the exact same. I can't resolve the differences between them. But if I go to this guy right here, I'm not going to detect any attenuation here, but I'm going to detect twice the attenuation here. Twice the attenuation. So this square I can resolve, and I can say that based on my reading, I would necessarily have one square attenuated here and one dense material here. So this square I was able to resolve. Good job. But what do I do about these two squares? These two squares, I can't tell them apart, and it just so happens that what we do in the CT is that we just add another way of radiating it. We're just going to add another axis, so to speak, and I'm going to radiate it. If I radiate it from this direction, and this direction, and this direction, and I place detectors here as well. It got a little bit messy, but what you can pretty much figure out is if I add another dimension and I radiate it from this direction as well, I would have enough information to say, hey, this column does not have any attenuation, so it necessarily has to be here. And on the other hand, here I may say, hey, this column has twice the attenuation, and by calculating, I can figure out that these are the attenuating squares. So basically, the computer tomography's answer to resolving what is the distribution of absorbing material in a square is radiating it from different directions and getting as much information as I can. And just so you know, when I take a given material and I divide it, into these squares are even in size. These are called voxels. I'm going to go ahead and put it right here just so we know what we're talking about. So these are the voxels, and one more thing that we need to understand is this is the long discussed equation to resolving the intensity from the X-ray presentation. And all this really means just a brief review, as if I'm radiating on this side. And some of this radiation, some of the intensity is absorbed here at some configuration, and some gets out on the other end. I can collect it, and I can configure how much is this intensity. How much is this intensity? Well, I can configure it by taking the initial intensity I had, by how much are these squares absorbing, their absorption coefficient, and what is the distance of the absorbing material. So let's think about it this way. Let's just say we're going to call this axis here axis A, and this is going to be axis B. I can add C and D, but we don't really need to do any further calculations because it's all going to be the same. And I'm guiding you towards questions they already asked. Let's just say square 1 absorbs, its absorption coefficient is 0.1 units. Number 2 is absorption is 0.2, and I'm just going to arbitrarily get them to increase. This is the absorption coefficient. This is the absorption coefficient. And the distance for all of these guys is going to be the same. It's going to be 1 millimeter. 1 millimeter. And then the question may be for an intensity of 1,000 units, calculate by how much the intensity entering row A, this row here, this axis here, is going to decrease on the other side. So basically I'm asked to configure the intensity at A. So intensity at A, and this is just by given by this equation, my initial intensity times E to the minus mu x. When we're looking at minus mu x, it's basically I'm combining square 1 and square 2. So it's minus square 1's distance plus, so I'm going to put the distance of square 1 times the attenuation coefficient of square 1, this is for square 1, plus the x and attenuation coefficient for square 2. This is basically what I'm doing. So I know the distance is going to be the same. The distance is 1 for both, and it's not going to alter this number. And for 1, my attenuation is 0.1, plus for 2, my attenuation is 0.2. So how is this going to look? My intensity at A is going to be equal to the 1,000 units of my initial intensity times E to the negative 0.1 plus 0.2. And this is easy. This is an easy mathematical equation to solve, providing you have a calculator for the exponent. And this actually was present in quite a few exams. So this is not that hard, and I can actually ask you to calculate what is the intensity going through here. And what you need is to add number 2 and number 4, and you can call this D or C or whatever way you want. So this is just a way to answer a question, just using this equation here. Very good. So we spoke about what voxels are. What we really have left to discuss is the the relationship we have between resolution and voxels and radiation dose, or we'll say radiation applied. And you may guess that if I have 2 units of the same volume, this unit is spread to, let's say, 2 voxels. And this has 2 voxels per, let's say, row. And this would have 5 voxels per row. If I analyze this and I radiate these, I may get better resolution the more voxels I have. I can get better resolution and better configuration than I can get with this. So obviously, the more voxels I have, and I'm going to put it down here, the more voxels I have, the more resolution I have. And now what we have left to discuss is the idea of radiation applied. In order to get all the information about the rows and columns of the voxels, what I really need to do is to radiate each row and each column. So here I have 1, 2, 3, 4, and this is just a basic idea. Let's say I'm radiating this body 4 times. Here I'm going to have to do it 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and here also 5 times. So the more voxels I have, the more radiation I would have to apply. So the more voxels I have, the more radiation. I'm going to put it right here. The more voxels, the more resolution, the more radiation I have to apply. So what you need to understand is we actually determine the size of these voxels. We can send this dude up to do a CT scan and say, well, I don't need such a high resolution on this one, so let's not set so dense, so high resolution small voxels. We can make do with slightly larger voxels, and by that we can decrease the radiation applied to this dude here. So we can actually determine. We can actually mix around and play with the size of the voxel to decide what radiation we apply, and that way we don't need to apply radiation that is unnecessary. And now I want to talk about the idea of attenuation, and we've discussed attenuation and absorption interchangeably, but we can break them apart. Attenuation is basically either absorption or scattering. And if you're looking at these terms and you're saying, oh, this is easy to understand, you're probably right. If I have a material here and a material here, if the energy is entirely absorbed, the incident photon is just going to be absorbed in the material. Whereas if I have a scattering effect, you may observe my photon coming in, imparting some of the energy, and then bounced off. So it's not entirely absorbed in the material. Those are just two different types of interactions of attenuation. And also, when we're talking about the attenuation of radiation, the most crucial factor that determines the attenuation, we're going to put crucial factor that determines the attenuation of radiation, is obviously the material itself, and in specific, the atomic number of the material, atomic number, or Z. So you can imagine that a hydrogen atom is not going to be absorbing as much as let's say carbon 12. Carbon 12 has an atomic number of 6, whereas hydrogen has an atomic number of 1. So carbon is going to have a higher Z, a higher atomic number, and it is going to absorb more. But not only is it just about the higher the Z is, it is Z to the third power. And what do I mean by that? I mean that it's really, really affecting the absorption. And I'm going to use this data here to make it more apparent to you. Let's just say that we have the respective atomic numbers of all these elements. But what we can see here is the column that represents this number to the third power. And this is really how the relationship is applicable. And you can see that when we're talking about, let's just say, nitrogen that has 7 protons, the number of protons to the third power is a pretty big number. And as we go down, we can see iron that we have in our bodies. It has a massive number to the third power. So this is really, 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 the Z to the third power is really massively affecting the attenuation of radiation. And if we take these two players here, iodine and barium, we can actually use them as what we call contrast material. Contrast material. We know that we have iodine naturally occurring in our bodies, and iodine, we can couple it with a biologically relevant molecule that, let's just say, is going to migrate in our bodies and slowly get to our thyroid gland. I'm just going to draw an object here. Let's just say it's attenuated and absorbed in this. We're going to do pink for iodine. Let's just say this is now filled with iodine. If I radiate it, it's going to considerably absorb the radiation more than its environment. So it's going to stand out. So anything that has a great concentration of iodine or a greater concentration of iodine is going to stand out considerably. And that is why this is called contrast material. I can inject it. It's going to migrate to a sort of tissue, gets absorbed there, and then that tissue is going to exhibit a high contrast. I'm going to see it very clearly. And just so you know, we can use barium as barium sulfate. We can use it to look into gastrointestinal absorption. This is just something you need to know, but it's something you don't need to know. But what you do need to appreciate is that the atomic number is the one factor that has the most impact on the attenuation of radiation because it's to the third power. And also we can use contrast material like, just remember one of them, iodine. We can use contrast material in CT. And we're going to keep on trucking. We're going to keep on trucking. Now we're going to talk about the Hounsfield units. And the Hounsfield units is just units that describe the different, let's say, the way in which different tissues, and this is not for different elements like carbon 16, carbon 12. This is for which tissues absorb in our body. And what we can see right away, and you don't need to memorize any of this really, what you need to know is that you have tissues like the cerebral spinal fluid, that their index is 15, and water that absorbs less. And you can see that blood absorbs quite well, maybe because it has a lot of iron in it, and muscles absorb pretty well, and bone absorbs really well because it's full of calcium that has a pretty high Z atomic number. What's really important to know about the Hounsfield units is that the Hounsfield units for water are always going to be 0, and the Hounsfield units for air are always going to be -100. You can think of these two numbers as a set standard to relate to the rest of the index. This is just like saying the set allowed legal highway speed is 100 kilometers an hour. That doesn't mean that you can't go, well, I'm not talking about legally, that doesn't mean that you can't go faster or slower. That just means that this is a set speed that is, so to speak, safe. So we can say this is a set standard that is, so to speak, can be compared to other indexes here to say, oh, it absorbs more than water, less than water, more than air, less than air. That is really what you need to know as far as the Hounsfield units. Hounsfield units, the way in which we can categorize how tissues absorb and attenuate radiation. And for water, the Hounsfield units is 0, and for air, it is minus 100. Hounsfield units, minus 100. And we're almost done. What we need to discuss is the mechanism. And there's different mechanisms, and in our presentations we have the evolution of CT machines over time. But what's really important to understand is, again, I'm just going to draw this in 3D. I have my CT machine here, and I have my, let's say this is the table my patient is on. And basically, let's just say I want to do a cross-section of my patient's abdomen. This is the abdomen of my patient. These are his legs. I want to do a cross-section of this abdomen. So how would this cross-section going to look? Well, this is going to be my specimen here. And I need to radiate it, and I need to read it. So I'm going to have a source. This is my radiation source. And I'm going to have detectors. We put the detector all around. Just imagine this is a circular tube. So if these two are in a tube, it's going to look something around. We're going to have a tube that contains these. Oh man, this is a horrible drawing. But this is the tube that you see here. And in the tube I have the radiation source, and the radiation source is just radiating on our sample. And our sample either absorbs or scatters the radiation. And the detector here can read the radiation. Maybe it has some scintillation detectors and photomultiplier tubes that we learned all about how those detect radiation. And basically what you need to think about is, we said that we need to radiate our object in different axes, from different directions. So the easiest way of doing this is just, hey, take this whole round thing and make it revolve. It's just going to turn. And as it's turning, the radiation source is also turning. It's going to radiate it from different ways. And this is really how a CT machine works. There are a lot of interesting exotic CT machines like the spiral CT. And all the spiral CT is really is the principle of having this thing turn, just like this that we discussed. You're going to have this tube turn. And and alongside this tube turning, you're also going to have this little surface pushed forward as well. And what that creates is it just minimizes the time of the imaging, the time that it takes to create the image. What you really need to understand from all of this mechanism idea is that you have radiation source, you have a detector across from it, You have the specimen in the middle, and these two revolve around the specimen. So they revolve around the specimen. And when I say specimen, I really mean someone, a person. And when we've discussed the mechanism, it's not too difficult. It was pretty easy. And this is how it really looks. This picture is brought to us by the webpage of Griff Wason, Art and Illustration. It's really a cool website. It may be worth your while looking at. But basically what we have here, this is our radiation source. Let me switch to yellow to get better contrast. This is our radiation source. And on the other hand, we have our radiation detectors. And you can see that this whole cylinder is revolving. It's just running around and turning, so we can radiate it from different directions. And if you want to understand what the spiral CT is, well, when this thing is turning, all you really need to do is just push the table forward, and then the cross section is going to take less time to image. That is pretty much it. And if we want to take a nice image brought to us by Wikipedia of the gastroentrails of, this is a CT image, and it's a really nice image. And I'm going to finish with the note of saying CT, and this is important to know, is an anatomic imaging method. And I promised you a video about the differences between anatomic versus functional. And we're going to do it after we finish off with the next imaging method, which is PET. But for now on, all you really need to know is CT is an anatomic imaging method. Hopefully you found this helpful, and see you on the next video about positron emission tomography.